Computational binding.
We have colored knowledge of every single pixel on the surfaces of objects, and each of these pixels can change to any color at any time. A voxel representation of knowledge of the surface of a strawberry could be represented in a computer as a 3D array with X, Y, and Z coordinates. Computer memory is architected in a line of memory locations, each with an address. The cells holding each of these 3D voxel values could be laid out in a RAM chip. Each of these pieces of information could be placed at random locations in the chip. None of these standalone memory buckets has any relationship to any of the other buckets. And of course, their relative location in the chip relative to other pixels has nothing to do with the actual location in 3D space those pixels represent. All the spatial relationship computation in a computer is done in the central processing unit, or the CPU. So the values need to be copied from RAM into the CPU, where they can be computationally bound and compared. This is showing 6 registers in a CPU, bound with the computational logic units. We may load a reference value needed to determine if the strawberry is ripe enough into one of the registers of the CPU. Then we can, one at a time, address the values of the surface of the strawberry, putting them into a CPU register. To give an idea of the complex machinery required to do even simple comparison, this is a discrete logic diagram of an arithmetic logic unit. This complex machine is only able to compare or do a difference operation on 4 bits of information. This logic diagram represents the complex wiring of about 170 transistors just to compare 4 bits of information, doing only one specific type of difference computation. Each specific operation must include a different set of discrete gates wired up differently. The complexity of the machinery between each register goes up exponentially as the number of bits in each register increases. It is this large amount of complex integrating hardware required to do computation between 2 values. The expense for that much integration hardware doing the integration of information is why there are only a small number of computationally bound registers in a CPU. If the 2 values are close, the difference will be a small number like 2. We need to temporarily see if the difference results. Continuing the process to determine if the strawberry is ripe enough, we can sum up all these differences in an accumulator, while counting the number of values, which will enable us to take an average of these differences of all the pixels. If the pixel belongs to a leaf, we can reject that voxel. After iterating over all the pixels, we have the number of pixels in the count register and the sum of all differences in the accumulator register. Computers cannot be aware of all the pixels at the same time like we can. So they need to compute intermediate values, like an average ripeness value of all the pixels, so the computer can make a computational decision to pick the strawberry using only the one average number representing the ripeness of the entire strawberry. In this case, the average difference of the entire strawberry is less than the threshold required to be ripe enough to pick, so we decided to take the pick strawberry branch, based only on the single average value representing the entire surface of the strawberry. The computational binding is very different from this type of communication. Communication is done from afar and must be substrate independent. Each different representation of the abstract information must have a functioning piece of transducing hardware, performing the dictionary interpretation to the correct representation in the next link in the chain. This type of mere transduction communication does zero information integration or computation. Tononi's integrated information theory focuses on how important all this kind of computational integration is. The only thing that enabled computers to get by with this such small amount of data being computational bound at any time is their speed. While we integrate all of our awareness together, in parallel, computers need to come up with lots of intermediate values, like the average ripeness of the entire strawberry, before we can make the decision to pick it based on that single intermediate average value. Before, we pointed out that if we know the color of something, that colored knowledge must be something. Similarly, if you are aware of a relationship between two things, there must be something that is doing the computation that achieves that intuitive awareness of that relationship. In this example, we iterate over all the pixels of the strawberry one at a time, continually accumulating the total amount of differences of each pixel from what we want. Communication like this is very different than the computational binding. If something is aware of the ripeness of a single pixel through some computational binding, there must be something that is performing that computational binding. Neurons are slow, so we compute all this with extreme parallel processing and computational integration. Instead of lots of sequential intermediate calculations, we are simply aware of all of it in parallel, giving us our extreme real-time situational conscious awareness of this computation going on all at the same time. With only a few registers in the CPU that can be computationally bound, the computer requires a lot of intermediate results to enable things like collecting averages of differences, all of which can be iterated through at blinding speeds. But with consciousness, we are just aware of the entire situation and all the relational values and intermediate differences in color, all at the same time. If a single pixel changes in value, a CPU would have to wait till it gets that single pixel and can load it into the CPU before it can be aware that that pixel has changed. But with consciousness, we know immediately if any one of those pixels changes in value. There must be something that is doing all of this computational awareness, not only between each pixel, but there must be complex binding with each pixel, and all the higher level awareness of what each pixel is a part of and the implications of such. All this awareness doesn't come by magic. If the intrinsic quality of any of the pixels we are aware of changes, the entire system is aware of it, resulting in everything being affected by the qualitative change of the intrinsic quality of that one pixel. The instant that one pixel in the center of the red strawberry changes to green, not only are we instantly, in parallel, aware of that change, we are consciously aware of the fact that that changing pixel is now a different color than the rest of the strawberry, and that it is now the same color as the leaves. We don't need to iterate through all the pixels yet again to finally find that one different pixel, as would be required with a minimally bound abstract CPU, iterating through all the pixels over and over again. Not only are we instantly aware of the fact that that one pixel has changed and how this is different or the same as the other pixels, we have information bound into our consciousness of the significance of that. As we watch this video, you know the video recording has simply been altered to toggle that one pixel. No big surprise in that experience. But if you were in the strawberry field and noticed a pixel on a single strawberry flashing like that a strange thought would likely enter your mind. Some people say science isn't so much of a eureka moment. It usually starts as more of a that is strange thoughts, where something isn't jiving with your predicted knowledge of physical reality and its falsifying consequences. You would want to pick the strawberry and look at it closer. You would likely want to show it to someone else and see if they could see that changing pixel. If they couldn't see that changing pixel, you would start to wonder about your own sanity, or at least your conscious knowledge and why you're experiencing that. We start out with the belief that our knowledge is reality and that redness is an intrinsic property of the strawberry. Experiencing visual changes that nobody else could see like this would be very falsifying evidence that that point on the surface of the strawberry was actually changing. If you had knowledge of a changing pixel, that knowledge must be something different than the strawberry out there, and your knowledge must be changing, even though somebody else could see your knowledge of it changing. Another theory that might computationally bind into your consciousness while this is happening, which might explain this exception to your normal understanding of physics, would be something like, am I in a matrix? Has someone hacked the physics of what is being communicated from that matrix? Is someone on a lower level of physical reality than our simulated matrix level trying to get my attention? In the Matrix movie, we are surprised as we see a kid breaking the laws of physics by bending a spoon with the power of his mind. The kid makes a truth claim that there is no spoon, and that it is not the spoon that bends, it is only yourself. If there really was a matrix, that would be a truth claim. It is only the knowledge of the spoon, part of ourselves, in our brain, in the vats, which is bending. Though we must still accept the fact that even if there is no real spoon out there, there must be some kind of matrix or something simulating a real spoon out there in a way that enables both our eyes to objectively see the bending spoon in a way that gives us conscious knowledge in ourselves of a spoon that is bending. As Descartes pointed out, the belief that there is a real spoon out there which we can all see could be doubted, as is being claimed in this scene. But if we are able to achieve a neural ponytail and computationally bind to it, and directly apprehend things outside of ourselves, this could demonstrably falsify claims like, there is no spoon, only ourselves. And more importantly, it would let us directly experience what color that spoon really was, not just what color that spoon seemed to be. Our consciousness is specifically designed so it seems to us that the quality of our knowledge is actually the quality of the strawberry. Whether you believe we were intentionally deceived by some god about the nature of perception, or whether manless evolution resulted in the same, seeing such an optimized and simplified way of thinking was more efficient, making us more fit. The fact remains that something has gone to extreme efforts to perpetrate this false, naive and simplified view of reality on our conscious knowledge and the way we see it. The difficulty in seeing through this deception is a big part of why it is so hard to understand consciousness. But if we want to understand our consciousness, with a hope that we might soon start improving it, we must achieve a higher level of understanding. When any one pixel of our knowledge changes color, there must be something in the brain that is that physical change of that one pixel of knowledge along with all the other points of knowledge we are consciously aware of. And if the entire system is aware of the meaning and implications of that single changing pixel, there must be something that is performing that computational binding, which is our conscious situational awareness. This kind of mass parallel computation where everything is aware of everything else could theoretically be achieved by some kind of quantum entanglement, as predicted by the Penrose-Hameroff orchestrated objective reduction theory. Another possibility with significantly more consensus would be the harmonic resonance or standing waves in neural tissue predicted by Stephen Lehar and the many other harmonic resonance theories being written about more every day. In addition to not needing transducing dictionaries between physically different representations of color to preserve meaning, this kind of wave computations running directly on intrinsic physical qualities is likely far more efficient, almost magically so, especially in large integrated ways than the discrete logic gates we must use in traditional CPUs. Despite the possible, almost magical power of this kind of wave computation, this in no way means this kind of wave computation is any less capable. We define consciousness to be computationally bound elemental intrinsic qualities like redness and greenness. If we are not consciously aware of something, it is not being computationally bound, part of subconsciousness. When we recall it into consciousness, there must be some computational binding mechanism which binds this with the rest of the information we are aware of. We also just discovered this related polysynchronous waveform computations paper by Dr. Eugene Ezikovich brilliantly describing how computations can be done with waves, a possible subject for a future video chapter. Consciousness is what it is like for an extreme parallel CPU to compute directly on phenomenal physical qualities. And it is definitely like something for this parallel phenomenal wave CPU to compute. All there are in abstract computers are isolated strings of ones and zeros which can be grouped to represent words like red and green, which aren't intrinsically like anything. Unlike abstract words, it is definitely like something for a parallel phenomenal wave CPU to do computation.
Everything owes its existence solely and completely to sound.
We could use your support. There's a petition topic on Canonizer titled What Are Color Qualities? There is a link to the Demonstrate Subjective Qualities consensus camp in the description below. It would help if you would sign that consensus camp.